we can make a model of our vibration absorber system as the diagram on the right shows. So we have our main machine as it's labeled, but it could be a building, it could be some other originally 1 degree of freedom system with a deflection of x1. And this oscillation of x1 or deflection of x1 is what we are ultimately going to want to limit. So here we're modeling it as an undamped system because that way the natural frequency is going to be where resonance is occurring directly. If x1 is what we want to limit, what we're going to do is add this vibration absorber attached to our main machine or our main mass. And when we put on this vibration absorber, we are going to have direct control over what K2 is and what M2 is. And again, this is premised on our main machine M1 having a mass that we really can't change and a K1 that we are unable to change. So we do get to select the spring constant and the mass of the vibration absorber that we're attaching to our main system. So now we're going to have 2 equations of motion as we are going to have 2 independent degrees of freedom in our new system. We have x1 and we have x2. So we can get the equations of motion for this 2 degree of freedom system now using Newton's laws or Lagrange's equations, either one that we're interested in applying. So we're going to premise this on our forcing into the system being a simple harmonic function here, just a sine function with a constant frequency and a constant amplitude, and that is only going to be directly applied on the main part of the system, M1. So again, if we're talking about an earthquake, this is a pretty good way to model it. It's going to be more or less a sinusoidal wave operating at a low frequency that's going to be applied directly to the base of our building, and our building is what we would be modeling as M1. But now that we put the vibration absorber on, this is a 2 degree of freedom system. And what we're looking at is an undamped 2 degree of freedom system with a simple harmonic input. And this is what we saw in the last subsection, how to get the steady state behavior of that type of system. So we can make the impedance matrix, we can solve it, we can invert it, we can then multiply it by the forcing, and we can get our amplitudes. And in this case, it would be purely real because right now we're operating with no damping. So applying those ideas from the last subsection, we can get those closed form amplitudes this way. So we get the amplitude of the steady state oscillations for x1, capital X1, and for x2, and then our steady state is going to be in the form we saw before of these amplitudes times sine omega t. Again, no phase difference here because we are treating it right now as an undamped system. So we see here the amplitude of our oscillations. We see the amplitude of x1 and the amplitude of x2. Now, they actually have the exact same denominator. It's going to be impacted by the 2 spring constants, the 2 masses, and the driving frequency. But we see that the numerators are going to be different. The numerator of x2 is only going to be impacted by the amplitude of the forcing and the spring constant that we choose for our vibration absorber. However, x1 is impacted by the K2 we choose for the absorber, and it's impacted by the mass and the driving frequency. And this is going to be important in how we select the design for our vibration absorber. The fact that these numerators are different and the fact that the numerator of x1 is going to be determined by the driving frequency and both of the design parameters that we choose for the vibration absorber. And I have details in the Mathematica file of how I got the x1 and x2, but again, it's just coming from what we saw in the last subsection on simple harmonic forcing on undamped 2 degree of freedom systems. So how do we choose the design, that is the K2, the M2, for our vibration absorber? Well, the idea here is that really what we are trying to minimize is the motion of that main mass, M1, that originally 1 degree of freedom system that we thought was going to experience a large amplitude of oscillation when the driving frequency, the driving function, was applied to it. So by adding the vibration absorber, our hope is that the amplitude of its oscillation is now much smaller. So, and ideally, it would be 0. So it'd be great if in our building example that we'll carry through here, we had the vibration absorber and we have a 1 Hertz frequency earthquake come in, and the amplitude of oscillation of the main building is 0. It's not swaying at all in the presence of this earthquake. So mathematically, what we want is that x1 to be 0. So we can set it to 0. We are assuming by using this equation that at this specific driving frequency omega, we are setting our amplitude of oscillation of x1 equal to 0. So under that assumption, when we set this equal to 0, we can solve for an m2 and a k2 that are going to make this term in the numerator equal to 0. And we have an infinite number of choices of m2 and k2 we can choose from that will make that numerator 0. So basically what has to happen? Well, the ratio of the k2 to m2 that we choose has to be equal to the driving frequency squared. And under this assumption or under this design, we, without the vibration absorber, said that the original 1 degree of freedom system had its natural frequency at the driving frequency. So that meant in the original 1 DOF system with its K1 and M1, K1 over M1 was equal to the natural frequency squared. So here, this omega n, that's the natural frequency of the original 1 degree of freedom system. But keep in mind, we are introducing a second natural frequency in the 2 degree of freedom system, and both of them are going to be different than that original natural frequency we had. So again, just to reiterate, when we can set x1 equal to 0, the original system was being driven at its natural frequency, the original system being 1 DOF, and now what we're doing is adding that absorber so that the 2 new natural frequencies are away from that original driving frequency. And again, I want to reiterate, when we're setting x1 equal to 0 in this equation up here, this is for just a single driving frequency that we are trying to avoid having our 2 natural frequencies near. In other types of problems, there might be a range of driving frequencies that we don't want to be operating near. We don't want to, in that case, simply set x1 equal to 0. We're going to see that it could introduce other problems, as we're going to see in the example.